We just saw earlier on this page why we like for a basis to be orthonormal. We know that an orthonormal basis has nice projection properties, and in fact, projection is the same thing as representation. And so if we ever wanted an easier way to represent a vector, an abstract vector, in terms of a basis, if we use an orthonormal basis, we have a nice, easy way of doing that just by a single inner product. So now that we like orthonormal bases, let's look at how we can always construct an orthonormal basis. This procedure is just as important in linear algebra, maybe only second in importance to Gaussian elimination. And in fact, just like when we solved systems of equations, we did row operations and we found an LU factorization of a matrix, we are going to find that this is also going to be equivalent to a matrix factorization. So now here's the idea. Remember that we could take a vector v and decompose it into projections, two perpendicular projections. This is the x, y, z coordinate system, and so picture this vector v being on the xy plane, like on the plane, xy plane. If we could find the projection of v into the x direction, do we remember how we found automatically this opposite side of this triangle? It was called the orthogonal projection. Do you remember how we did that? Is we took the vector v and we just subtracted the projection in the x direction. By doing that subtraction, by finding this and subtracting it, we automatically got this other side of the triangle, and that was by construction orthogonal. So this is the idea that we're going to build on to constructing this orthonormal basis. Let's build on it one more time with this picture. Here's how we're going to extend this. Now look at this vector v that's way up in the 3D space. We had these two vectors before that we found that are perpendicular to each other. How can we find a third one perpendicular? We take the new vector v, we just find any vector v that's in 3D space. Remember, we couldn't do that in 2D, but now that we have any 3D vector, we can subtract the component in the x direction, the projection into the x direction, and also subtract the component in the y direction. So there's two projections that we subtract. And then what we're left with is the third final component. And look, this is in the parallel to the z-axis. It is perpendicular to both of the original two. So now looking at the handout, the problem that we're looking to solve is given a basis, any basis, that we call the AIs. That would be like any three independent, not parallel, but three independent vectors in 3D space, but a basis of AIs. We're going to construct perpendicular vectors that will also then, because of some theorems that we saw earlier in the handout, orthogonal vectors are automatically independent, meaning that they are automatically a basis. We just need to find them. This is how we're going to find them. The strategy is that we're going to compute each qi by taking the new ai. Before we had an a2 that was down here. This is what we'll call the a3. We're going to take the new ai and subtract all of the previous projections. See in that formula AI inner product with QK hat? Those are the projections. The inner products are the projections. Go back and look at those formulas if that doesn't make sense to you. Replay. So subtract all the projections. That's going to give us our new QI, which is the new orthogonal vector. And then there's a second step there. We will normalize as we go. It's interesting that we don't need to normalize as we go. If we don't normalize, then we're doing what we call Gram-Schmidt orthogonalization. If we do normalize, we're doing what we call Gram-Schmidt orthonormalization. Now, every example on this handout is going to be Gram-Schmidt orthonormalization, and that is because the inner products become easier to do. The numbers, warning, the numbers are not going to be as easy to work with, but the upside of that, the value of that, is that the inner products will be easier to do. So now, if you want examples of Gram-Schmidt orthogonalization without the normalization step, there are some of those in the textbook. And you'll see nicer numbers, but longer calculations with projections.